over lunch, one other question came up, and I don't know if you want to field it right away or if you're planning to revisit the target optimization process. But if you are going to revisit that, the question is really, is that optimization unique, or is it a chance you could get trapped in a local optimum when you're looking for that?
So that might be a good question. Ryan, are you on? Yeah.
Yeah. So, I mean, I can answer that. You're not ever guaranteed to get a global optimum. In the kind of problems that we see, you usually do land there. There's not a lot of local minima that you get trapped in, but it is possible to get trapped there. So if you feel like you might be doing that, you can start at different points, like just in the profile, or move the points around, and it should start at that spot to do the optimization. But usually it's, again, no guarantees, but in practice, I don't think happens a lot.
And so, just to follow up on that, we're minimizing the squared integrated, or the integrated squared difference. Is that right? Or
yeah.
Okay. So if you think about basically the distance from the fitted function to the target function, we're minimizing that. Yep.
Okay, well, I'm going to suggest that at some point, if you guys can do it, do it. But if not, I think one or more of the case studies I have has that optimization, and maybe we turn on to show the additional profilers that are involved with that optimization. So if it makes sense to do it as you guys are going through the afternoon, let's try to do that.
Okay. I don't have an example for that, so we'll make sure to leave time for you, Tom.
Okay. All right. Are there any other questions in the room?
If it's possible to go back and look at the Savitsky-Golay filter example, are we ever worried that the way that it fits to a polynomial might reduce or increase variability in the data that isn't intentional?
Yeah, so let me pull that example up. Okay. So let me just pull up let me pull this one up. Okay. So the question is, are we concerned that it's increasing variability? Is that am I
or just changing variability that is not attributed to noise necessarily?
Yeah, I do think, I mean, that's a reasonable concern. So when we do the Savitsky-Golay filter in JMP, what's happening behind the scenes is we're trying linear, we're trying constant, we're trying quadratic and cubic polynomials behind the scenes, and we're also varying that window width, and we're using an information criteria to pick the one that's the best, right? So the reason why I mention that is that by using the AIC to pick the best of those polynomials, the hope is that we're not overfitting too badly. So hopefully we're not reducing too much of the variation that's there in the data. But any type of smoothing like this, that's still a risk that we would sort of wipe away some of the important features in our function, which is one of the nice things about the way Ryan has done this in JMP, is that it makes it really convenient to sort of go back and forth to see how the function looked before and after filtering it. So that's kind of a safety check that you could just double check that we haven't over smoothed the function.
I guess you're good to go on picking up your content for the afternoon.
Okay, cool. So just to sort of pick up where we left off, I wanted to pull up this example where each column is a different resolution basis function for this quafflet 5, right? So resolution 1, the 2 resolution 2 basis functions, and the 4 resolution 3. So again, we can plot these to sort of see what those functions look like. But what I also wanted to do was just to look at a distribution of those basis functions as well. And we can see that for each one, the mean is 0 and the uncorrected sum of squares. So essentially the sum of squares of each basis function is 1. So they're all centered and sort of scaled the same. And that's important. We'll see that later, because it's kind of like when we're building a regression model. If we have 2 variables that are on different scales, we'd have to be careful comparing their regression coefficients. It's dangerous to compare variables that are on different scales. But that's why it's important here to keep in mind that the wavelet basis functions are centered and scaled similarly, so that when we go later to compare wavelet coefficients, it's okay to compare them because they're all on the same scale. I also wanted to point out, if we look at correlations between these basis functions, they're all 0, right? So resolution 1 is independent of the resolution 2 basis functions, and they're independent of the resolution 3 coefficients. So everything is orthogonal to each other. And earlier we sort of touched on one of the characteristics of wavelet functions is that they tend to be orthonormal. So here we see the orthogonality, and just a second ago we saw that they the sum of squares was 1. So those are important things to keep in mind. I also thought these scatter plots are kind of cool. This looks kind of like the Star Trek logo. I didn't watch Star Trek, so I don't know exactly what it's called, but that's what it looks like to me. Okay, so let's get back to the slides. Alrighty. Okay. So I also wanted to go sort of step by step and see how a reconstruction, the wavelet reconstruction works as we add resolutions. So like I said earlier, the resolution 0 wavelet is essentially just a mean, and that's what we see here. And then when we add the first resolution, we have a single, change point between high and low, and it adds a single, it's just a single basis function. Then when we go to resolution 2, we have unique features on the left and the right, because we've essentially split our data in half, and we have some freedom on the left and the right. And we just keep dividing our data in half and fitting that step function on each side. And we go, and now we add 8 more basis functions, and 16 more, and then 32 more. And finally, even with just 128 points, now at resolution 7, we've gotten up to 64 basis functions. So every 2 observations, we've got something that can handle that's addressing just those 2 observations. And it kind of helps to overlay them like this. So we can see the contribution of resolution 1, again, is just this, it's almost like an S function. And then we have higher, these lower resolutions are big features. And then finally, when we get down to resolution 7, that's where we see really local behavior. And again, I've really sort of harped on that. but those local changes are what makes wavelets really powerful. And then we put it all together. And here on the right, you can see that we've reconstructed the data really well. And then this is just a GIF that does the exact same thing for the quafflet, but it's helpful to see how adding resolutions to a different mother wavelet changes the reconstruction as well. And if you were paying close attention, you might have realized that when the reconstruction function stopped changing right at resolution 5. So when we'd go to resolution 6 and 7, nothing really happened. And you can see that really well when you overlay these resolutions. You can see a lot of local behavior here. And then at resolution 6 and 7, it's just flat. Those resolutions don't contribute anything to our final function. And there's a good reason for that. So let's look at the case of just 16 observations. With 16 observations, regardless of which mother wavelet we choose, the first resolution adds one parameter, the second resolution adds a parameter, then 2, 4, 8. And that's 16 total, right? So we had 16 observations, and we're using 16 wavelet coefficients to model that. Well, if you think back to if you've ever taken like a multiple linear regression class, if you have 16 observations and 16 parameters in your linear regression, you're going to predict perfectly, right? You're always going to be able to sort of reconstruct the original data. And it's the same situation with wavelets, right? If you use all 16 of those wavelet coefficients, we're going to perfectly reconstruct the data every time. But that's not terribly useful, right? If I ask you for a decomposition of my function to sort of simplify it, and you just give me back my data, we haven't really learned anything about the function that we're looking at. So one thing we could do is just throw away those last two resolutions, right? I don't think I need all of the resolution 3 or 4 wavelets. I can just set those equal to 0 and focus on 0, 1, 2. So now if I do that, I only have 4 wavelet coefficients in my model. I won't perfectly reconstruct my data. I'll get something much more meaningful. But by throwing away those high resolution basis functions, we're no longer able to act locally, right? Those small changes on our data, we completely lose the ability to pick that up. And that's a shame because that's one of the really nice things about wavelets, as we've mentioned a couple times now. So ideally, in a perfect world, we'd like to just drop those resolutions or specific components of each resolution. So here, I need all of resolution 1. I need the first resolution 2 basis function, but I don't need the second. And when I go to resolution 3, I don't need the first 2, I just need the second 2. Ideally, we'd like to be able to pick up that kind of behavior just based on the data, right? Let the data decide which resolution, which elements of each resolution we really need. And then we could avoid overfitting. We won't reconstruct the data perfectly every time, but we're not going to give up that local activity that we care so much about. So there's been a lot of research about how to do that, right? So after you do your wavelet decomposition, how do we throw away those components that we don't really need? There's been a lot of papers written about this. If you do a Google Scholar search, there's almost 100,000 results related to thresholding those wavelet coefficients. But the one that we've settled on in JMP is called the universal threshold. And it came out of Stanford. The author's name is David Donnelly. But the idea is we do our wavelet decomposition. We get all of our coefficients, and then we soft threshold them. which really just means some of them we set to 0, some of them we shrink towards 0, right? And then that gives us a new version of our wavelet coefficients, and then we can use those for reconstruction, right? Some of them will be 0, a lot of them will be non-zero, and we'll get something much more meaningful. And so this is what we've implemented in JMP. So when you ask for wavelets in the Functional Data Explorer, we're behind the scenes, we do the wavelet decomposition, and then we use this universal threshold method. But if you were to use R or Python, I'm sure there's implementations of the universal threshold there as well. And so part of that universal threshold is we need to solve for this lambda parameter, which is just a function of the estimated noise in the data scaled by the number of observations. And if you're not familiar with that soft thresholding function, it's okay. I was thinking about it when I was eating lunch. It's kind of like, you know, with my, well, I don't have a teenager yet, but I almost have a teenager. And if she were to ask me for $5 to go hang out with her friends, if I only had 3, she would take it, and I would have no money left. But if I had $10, she would take 5, and I'd be left with 5. That's kind of what this soft threshold does, right? Up until that threshold, it'll shrink everything all the way to 0, and then it'll just shrink things towards 0 beyond the threshold. And if you're familiar with variable selection problems or penalized regression, it's the soft threshold is exactly the same idea as what makes the lasso work, right? So if you apply the lasso penalty, it's working in a very similar fashion to this universal threshold. And then, so when we apply that, it'll zero out some of our coefficients, right? So we can see that here we have some zeros in our wavelet coefficient, and that corresponds to sections like this, where the resolution 5 reconstruction is exactly equal to 0. And we have another one here, and another one here, and then the entire end is sort of zeroed out. And that's exactly what we want. We only want things to be changing where the data really need them to be changing. And so that's a much more meaningful decomposition there. And as we saw in that quafflet example, it can actually wipe out entire resolutions. So for that example, all of the resolution 6 coefficients were equal to 0, and that's why it didn't contribute anything to the reconstruction. So it makes our wavelet decomposition a lot simpler. I wanted to add a couple details. We've touched on this a couple times already, but we have to assume that our data are on a regularly spaced grid. We also have to assume that regularly spaced grid is a power of 2, right? So if you have 32 observations, that's great. If you have 23, that's not so great. And it also means, because we've placed our data on the grid, wavelets, you know, right out of the box aren't necessarily great at extrapolating. There have probably been extensions to wavelets that I'm not familiar with that are more in tune to extrapolating beyond the range of the data we've observed. But at least though the way that we've implemented them at JMP, they're more appropriate for interpolation than extrapolation. And I've got to share, I mentioned I have an almost teenager, but I asked my middle schooler, I was so proud of making these memes, and I asked my daughter what she thought about them. And I was excited. I was hoping she would be excited too and tell Dad how cool he was. But she was like, Dad, that's so lame. That's not the Drake meme. Why aren't you using Drake? But yeah, it's very similar, but using a character from Star Trek, or to me, the guy from Reading Rainbow when I was a kid. But not all is lost if your data don't satisfy those requirements, right? So on the left, our data are clearly not on an equally spaced grid, but we can probably sort of just force them onto a grid, and it's fine. Um, Depending on your problem, that may be inappropriate to do that. But a lot of times it doesn't really change the meaning of the analysis if we just sort of fudge it a little bit and pretend that our data actually were equally spaced out. Another issue is that whole power of two. Don't worry about that at all, because we can just extend our function artificially, and there's a couple of ways to do that. So here we've got 23 observations, but we just need to get to 32 in order for the math to work out when we do the wavelet decomposition. So one way to do that is just to pad that last value, right? So this is our 23rd observation. We can just fill that in until we get to 32. We can also just add in the mean. We can calculate the average of our first 23 observations and add those to the end of our function. We can repeat the function, so we get to the 23rd observation, and then we start back at 1, 2, 3. You can kind of see we're just repeating the function here. You can also reflect the function, right? So this is 23, and then 24 is actually equal to 22, and then so on. And it's as if we just sort of folded it over and reflected the function across the x equals 23 point. And this is what we do in JMP. I feel like I've read that this is the most popular strategy for extending functions so that you can do the wavelet transform. We did experiment with some of the other ones, and this seemed to work the best. But when you're using wavelet software, whether it's in R or JMP, you don't even really need to know that this is what's happening behind the scenes. It just sort of happens and then handles it for you. Another thing I wanted to mention is a lot of times it looks like our data are nearly perfectly fit, right? We can see it's not quite perfect here, but in general, this wavelet on the left fits our data very well. And that's true in general. Wavelets do tend to fit really well. But if you zoom in, sometimes you'll see some funky behavior like here. When we think about doing least squares, right, we don't tend to see cases where we always overestimate, but that can happen with a wavelet because we're not doing least squares. So it is kind of weird that here on the ends, we sort of always overestimate the data, but that's sort of just an artifact of the way that the wavelet transform works. Sometimes we get a little bit of strange behavior on the extremes, either at the beginning or the end of the function. I would suggest that for small functions, the wavelet transform doesn't tend to work terribly well. If your function is, my rule of thumb, which is truly just a rule of thumb, is if I have 15 or more observations, that's when I start thinking, okay, I'll use a wavelet to model my data. If you have 10 or fewer, it's a little bit dicier, and I would tread carefully there. So to Tom's point earlier, when we talk about wavelets, there's a whole lot that covers a lot of ground. There's the simlets, there's the Haar wavelet, and they have lots of different shapes. And maybe you know that your data sort of look like a step function, and then it would be appropriate to use, then it would kind of be a natural choice. I want to use the Haar wavelet. Otherwise, a lot of the other wavelet functions are quite similar. Some of them have sharp peaks like this one, but a lot of them, it's kind of hard to tell the difference. So we want to be able to choose these. And what we do in JMP, and what I think is a good strategy, is just fit a handful of wavelets and see which ones fit the best. We can always calculate a sum of squared errors. It's just our function, the sum of our function minus the predicted value squared. And then we have a measure of complexity for our wavelet decomposition. So after we apply that universal threshold, we have a number of parameters. It's the number of non-zero wavelet coefficients. So we have a sum of squared errors, we have a number of parameters, and we can plug those into an information criteria like the AIC or the BIC and use those to compare the different mother wavelets, right? So when you're talking about the AIC or the BIC, smaller is better. So you can fit the HAR wavelet, the SIMlet, all of those, and just see which one has the best AIC or BIC, whichever model criteria you prefer. Just go with the one that fits the best. And then you don't really have to worry about, well, what's the difference between a SIMlet and a quafflet? I've been working, I implemented these and I've been working on them for a long time. I don't really know the difference between them, but we can assess how well they fit and just go with the one that's most appropriate. Yeah, so if you're using JMP, we fit 15 different wavelets and we sort it so that the best one is at the top, and that's kind of what we go by default. And we'll see an example of this in just a second. In fact, now we'll see an example now. Okay. Well, before I get into examples, Tom, were there any questions?
I had a question for you, or more of a comment.
Yeah.
When you were talking about you use wavelets for 15 plus points or more, and if it gets down to 10, it gets really dicey. I think when you get down to, under 20 or so, you're in the realm where I would think things like even the penalized spline methods, that's not an intractable number of knots. I think wavelets for me have worked well when I've had, spectra where we're talking about, there can be 1,000 or more points that make up that spectra, and there's lots of peaks, and that's where I think the wavelets really shine. So, if you had any comments on size of the, string of points that I was saying there.
Well, it might be easiest just to look at an example.
Great.
So here we have a single spectra from an olive oil, right? I sort of mentioned the olive oil example earlier, but here is a single spectra. So we've got a single function with 4,001 observations. So first you might want, well, I guess I should show the data. So this is what the data look like, right? So the first inclination might be, well, I'll fit a B-spline. And Ryan sort of touched on this earlier, but one of the cool things about the way he has implemented B-splines is it gives you an initial set of knots, but you can grab them and you can move them. So the initial set of knots may not have been ideal, but I'm going to move them so that they line up better with the peaks, right? So I can do that. And then you press update models and it'll refit using those knot placements. Now, it still doesn't fit terribly well. So B-splines are not really the right option for this data set. So we'll take those away and we'll fit P-splines. So now this fit looks a whole lot better. But if we look at some of these diagnostic plots, you can see a little bit of funky behavior, right? So these are our predicted values on the x-axis and the observed values on the vertical axis. You can see a little bit of, it almost looks like a cyclical behavior there. And then you see it as well here in the predicted by residual plot. So we can zoom in a little bit. And so I mean, it feels like up here, it feels like the P-spline fit pretty well. But when you take a closer look, it really looks like maybe we've missed some key features in that function, because it looks like there's some patterns in the residual plots, right? So to Tom's point, we have a lot of data. There's sharp peaks. This is really a great time to try using a wavelet. So I'll load those in. And you know what? I want to make sure it looks like what I expected. So I'm just going to run my script. But you can see it happened almost instantaneously, that it did the wavelet decomposition for all of these different mother wavelets. And based on the BIC, this Simlet 20 fit the best, right? Because if we looked at our coefficients, we have our father wavelet. Earlier I called it the coarse wavelet coefficient. Either one is fine. We've got resolution 1, 2, and then we have 4,000 total of these coefficients, right? And once you get into the higher resolutions, they're almost all zeroed out, right? And we only have a handful of high resolution coefficients. So the number of parameters for this Simlet 20 is just the number of non-zero wavelet coefficients. And that's how we can calculate an AIC and BIC. So now let's look at those same diagnostic plots. So this predicted by actual, it looks much tighter on the 45-degree line. So it looks much more promising. And let's zoom in on the residuals. So we zoom in, we zoom in, and we zoom in again. And we're finally starting to see a little bit of non-zero residuals. But I've zoomed in so much that we've tricked the jump into thinking that the vertical axis is just between 0 and 0, right? So I've zoomed in quite a bit, and I still barely see any non-zero residuals. So that it was kind of hard to tell with this example, but the wavelet fit was much faster than a P-spline, and it's reconstructing our data much better. Yeah, so the reason why I reran this is I had hidden a couple of measures, but we provide a couple of different model selection criteria. So we use the BIC by default, but you can also ask for the AIC or the GCV, the generalized cross-validation measure. And one of the really cool things is we give you the best wavelet, which is the Simlet 20, but you can look around and see, well, the Simlet 20 fit better, but maybe I really like the Haar wavelet. I like that it's just a simple step function. So you can see what would happen if you used the Haar wavelet instead. And we can see we're not fitting nearly as well, but maybe we'd be okay with that trade-off. So it allows you, we give you the best, but we allow you to sort of check out the alternatives. Any questions about that before I get back into slides?
Hands up in the room, so go ahead.
Okay. Okay. So a question came up earlier about functional DOE and wavelet DOE. So that's what we're going to talk about now. So earlier, Ryan sort of touched on this idea of functional DOE. We've got factors probably from a designed experiment or maybe observational data. We have some factors that we think contribute to the shape of the functions that we've observed. And let's say we store those design factors in a matrix, right? We'll call that Z. And in fact, when we load those into a jump platform, we call them supplementary variables. So whenever you fit a wavelet or a P-spline or a B-spline, we provide these function summaries that are they're functional principal component scores. And that's how we reconstruct the function using these shape functions. So we can build linear models treating those FPC scores like responses, right? Ryan sort of stepped through an example of that earlier. So we could build a linear regression for that first column of FPC scores. And then for the second function, or the second column of FPC scores. And we can build linear models just like that to sort of predict the FPC scores and then reconstruct the function using our shape functions. And we can use the exact same strategy with wavelets, right? If we store all of our reconstructed functions in a matrix called y hat, we just do an SVD of that, and that's essentially how we do functional data or functional DOE. But with wavelets, we actually have an alternative. We touched on this earlier. We have a parameter for each resolution. Some of the, most of the resolutions have multiple coefficients. So if we have a data set with in functions and P observations, we end up with an N by P matrix of wavelet coefficients. And we can use those exact same supplementary variables to predict, instead of predicting the FPC scores, we could use those to predict our wavelet coefficients. So for resolution 0, we could build a linear model for the resolution 0 coefficient. For resolution 1, we could build a separate regression model for the resolution 1 parameter, and so on. And so then with all those linear models, the output of those linear models are just our predicted wavelet coefficients. And then we can use that predicted wavelet coefficient vector to reconstruct our function. And that's what we call wavelet DOE in the functional data explorer. But the big question is which one is better? And to be honest, Ryan and I, we don't have a great answer for that. Functional DOE, it works really well in general, but remember, these shape functions tend to be active over the entire region of our data, right? So our reconstructed function using functional DOE would be a weighted sum of these shape functions. And these are very active functions, right? There's no local behavior with these shape functions. So we've sort of sacrificed that part of a wavelet. Wavelet DOE should preserve that local behavior better. But it does mean that we're building a whole lot more linear models, right? Usually when we're doing functional DOE, the first couple of principal components capture a lot of variation in the predicted function. So we only need to build a couple of linear models. But with a big function like what we were just looking at, there could be hundreds of non-zero wavelet coefficients. And that would mean building hundreds of linear regression models for those wavelet coefficients. So it could mean more, it could mean more in terms of computation time or complexity. The benefit would be that wavelet DOE would have more local behavior like we'd hope for. But if if we're not looking for that interpretation, it may be better to use functional DOE. So let's take a look at an example of functional DOE. Let's see. So this is the fabled olive oil data set. So we have each row is a function, and we know whether it's olive oil, vegetable oil, or a blend of oils, right? And the idea is we would like to be able to know how the spectrograms change depending on what type of oil it is. And so I actually don't know if this is the reason why there was a paper about this this particular problem. But it wasn't long ago on NPR I heard that one of the things at risk because of the changing climate is olive trees. So as we're able to produce less olive oil easily, there may be incentive to try to people to try to pass off blends or non-olive oil as olive oil. So I thought that was pretty interesting. Okay, so first of all, what I want to do is find out how the type of oil changes the shape of the function. So I'm going to make class, which is either blend, vegetable, or olive. I'm going to make that my supplementary variable. So I'm going to make that my supplementary variable. I'm going to add all those columns as my spectra, and we'll take a look at the data, right? So we've got, so these are our data. I think the red functions are blends, blue functions are vegetable oil, and green are olive oil. So we can kind of quickly see with the data what those look like, how they differ, right? So the first thing I'll do is ask for a wavelet. And it looks like the Simlet 20 was the best based on the BIC. So from there, if we want to see how the functions change as a function, if we want to see how that spectra change as a function of whether it's olive oil or not, we would just go to functional DOE, and now we've got a model. So you can see what it did in the background was, if we look at our FPC scores, it's taking this first functional principal component, and it's modeling these scores as a function of the oil type, right? And this example, it's not very complicated. We just have a single supplementary variable, which is the oil type. But in general, if we had a whole bunch of supplementary variables, it's doing best subset. But because we only have one, it's not such a hard variable selection problem. But so now we can see how the spectra change as a function of the oil type, right? So if it's a blend, the spectra tend to look like this. If it's an olive oil, they tend to look like that, and likewise for vegetable oil. So we really quickly were able to sort of quantify how the oil type changes the shape of the function. Now, what would happen if we did wavelet DOE instead? So we'll leave that profiler open because we want to be able to see that, and we'll ask for wavelet DOE as well. So we get a pretty similar answer. The difference is, if we look at what happened, we built a linear regression for the father wavelet. We built a linear regression for this resolution 4 coefficient, resolution 6. We've built a whole bunch of regression models for those wavelet coefficients. But then the end product is very similar, right? We have a very similar answer here. So it's for this one, it doesn't make a huge difference whether you use wavelet DOE or functional DOE. So let's look at a little bit trickier of an example. I don't know about anybody in the crowd. Ryan and I both have, relatively young kids. They're not it pains me to say they're not as young anymore, but Ryan and I are both big fans of Disney World, and there was a website that that publishes plans about how to most effectively visit Disney World so that you get as much done as possible. It's as you guys probably know, Disney World is not a cheap place to visit, and you want to be able to do as much in as little time as you can. So this website sold plans about how to properly visit Disney World, and for a while they made their data publicly available. Unfortunately, it's not publicly available anymore. But what they had, and this is for just one ride. This is a ride called Slinky Dog Dash, which is a really fun, like family roller coaster. But what they had was the wait time throughout the day for multiple years of data. And they also have all kinds of other data, like whether it was supposed to rain, whether it rained yesterday, what day of the week, all of that information. So when I found this data set, the first thing I thought was, I want to figure out if we can model the wait time as a wavelet. So let's try to do that. So the first thing is just getting the data into Functional Data Explorer, right? We have date, we have hour of the day, and then we have the posted wait time, right? So don't show up when the posted wait time is 270 minutes. That's pretty brutal, especially in June in Florida. You don't want to be outside for almost 3 hours or 5 hours. But so you can see this is the very first day that this ride was open. The wait time was almost 5 hours for the entire day, and then it finally dropped, right? But for each cell here is a day, and this is the wait time throughout the day. So, and we have multiple years of data. So the first thing we can do is we can fit a wavelet. And even with years of data, that fit really quite quickly. And we can see if we just scroll through a handful of these, that the wavelet reconstruction is really quite good for each of these days, if we're just sort of spot checking it. So now, I didn't really mention this, but I loaded in day of the week, month, and year as supplementary variables. And I want to be able to predict the wait time based on the day of the week, month, and year, thinking that there's not much you can do about the year, right? Time is only going forward. But if there's certain days where this ride, certain days of the week where the ride is less crowded, or certain months, that might be the right time to visit so that we don't have to wait in line for 5 hours. Maybe we could just wait in line for 1, which is still pretty rough. But so in order to take advantage of those supplementary variables, we're going to do functional DOE, right? So what is happening behind the scenes is it's taking these shape function, or it's taking these FBC scores again, and it's predicting those so that we can use these shape functions to reconstruct those wait time curves. And some of these, as you go down the line, are actually really interesting. So this component here, Think about it's really crowded in the morning, and then it gets less crowded, and then more crowded, and then less crowded. And I kind of see that as like people check the wait times, and it's really long, so they don't get in line. So the wait time goes down. And then people see that the wait time is down, so they go get in line, and then the wait time gets real long again. So it's kind of this interesting bouncing up and down for a lot of these features. Um, anyway, so those are sort of the building blocks that will help us reconstruct our function when we called functional DOE, right? So what we end up with is so this panel here is the wait time throughout the day, and we can move this around and see which days are less crowded, right? It seems like probably Wednesday is the least crowded time of the week. Um, March tends to be quite crowded because that tends to be spring break. And then you can see how it changes as a function of year. Now, something funny happens in 2020, March of 2020 to be precise. The wait times went way down. In fact, they dipped negative. But I think we all know why that happened. But yeah, it really quickly allows us to see how those wait times change as a function of things we really care about, like day of the week, month, and so on. So a lot of times you can see a dip here in September. If you're willing to go to southern Florida, or I guess central Florida in September when it's really hot and humid, and a hurricane may cancel your entire trip, you'll at least enjoy shorter wait times for this particular ride. And let's also, so that was functional DOE. Let's also try wavelet DOE. And again, it's a very similar idea. It's just now, again, we're modeling these wavelet coefficients instead of principal component scores. But again, we kind of come to very similar conclusions. If you look at 2021, this is the last year that they made available before they took the data away. You can see that springtime was really crowded, and then through summer and fall, it got a little bit less crowded. So we came to very similar conclusions using both functional DOE and wavelet DOE. So that's a long way to say we're still not really sure which one of those is best. They have advantages. Functional DOE will tend to be a lot simpler. We can get a lot of the variation in our we can capture a lot of variation with just a few principal components. I'm not able to find that. Okay. So we tend to only need a couple of functional principal components to capture most of the variation. So it tends to be a little bit simpler to do functional DOE. But with wavelet DOE, there's a little bit more flexibility. There's a little bit more of a chance that we'll capture that local behavior. But so far we don't have any great examples saying that this is clear, wavelet DOE is clearly better for this example or this type of data. We just haven't been able to find that yet.
Clay?
Yeah.
I know you and I have talked about this data, and particularly I have a somewhat similar data set, several years of FAA data on Air Traffic Control Center, airspace counts, etc. And I haven't yet looked at that with the wavelet DOE. But I think in all of these approaches here, I would wonder how much people try to break the data into validation and test subsets, and create the models, both functional DOE and wavelet DOE, and then compare them how well they perform against, other cases, just to see if there's an actually improved prediction capability. To me, that would make me pick one over the other.
Yeah.
Otherwise, I think, as you pointed out, the functional DOE generally has fewer shape functions to it. It just seems simpler.
Yeah, you got it. That's a good point. We have tried doing some holdout sets and haven't found a huge difference between the two for the cases we've tried. But that is a good point, that you could use a holdout set. So maybe hold out like a month's worth of data and predict the wait time curve at those dates and evaluate how well each one fits. We haven't really done that for this example, but it's a good idea.
Hello, Dave. This is Curtis Miller, and I'd like to ask a question on this topic. I guess I was somewhat confused about what exactly the difference is, because I'm not entirely sure what is taking place. My thought would be that what's happening is that you're using wavelets as a basis to come up with a smooth representation of the discrete data points as functions. Then, with that representation, use functional PCA that then finds the principal component functions. Which the reason why it's coming up with similar representations is that basically by the mathematics of it, it finds the most efficient representation in a small number of functions, which is still being expressed in terms of your wavelet basis functions, but it's still finding the most efficient one. So I'm not entirely sure if there really is a difference between these two things. So I guess is it possible that the best thing is basically to be using both, where you're representing your individual curves with using wavelet basis functions, and then analyzing the data set across the different curves with the functional principal component analysis?
That tends to be what we recommend. Yeah, absolutely. And just to be super clear, we can sort of reconstruct what's happening. So we're gonna save these FPC scores, right? So now we've got these in a data set. So here's our FPC1, our FPC2. So just to keep this simple, I'm going to subset this. If I can find the subset button. Okay. So what I'm going to do is I'm going to model oops, that's not what I want to. I'm going to model this FPC score as a function of these predictors, right? Day of the week, month, and year. And just for simplicity, I'm going to use forward selection. So what I've got here is a model that uses day of the week, month, and year to predict the FPC score for new observations. And then using those predicted FPC scores with our shape functions, that's how we reconstruct these prediction curves, right? We take our predicted FPC scores and then use those to weight our shape functions, and that's how we get this final curve. So yeah, it's the reason. One of the reasons why they can lead to different results is these FPC these shape functions don't have a whole lot of blips in them, right? They tend to be quite global in nature, whereas wavelet coefficients can be much more local, like we saw with the examples earlier. They can impact a much smaller region of the domain, even though a shape function from the FPCs wouldn't necessarily do that. Were there any other questions, Tom? Or
We have one more.
yeah,
And just to keep in mind, I'm looking at the clock. We've been going about an hour, so consider in the next 10 minutes when would be a good break in your set.
Well, I had a statement and then also had a question. So I think maybe this is just my understanding of the functional principal components is that's basically a Kahuna web decomposition. So that yields the best basis in terms of total mean squared error, but the wavelet does not have that constraint. So best would be, what are you defining as best? What metric? So in mean squared error, sure, use a PC, but if your best is not something else, then you have to define what is your metric for best reconstruction. I think that would tell you which avenue you may go down. And then the question I had before is, when you had those plots of like weeks and then days of the week, how did you construct those curves like one more time?
which ones?
Those curves right
Yep.
there, yeah. How did you create those again?
Oh, so what we did, so for functional DOE, using the functional principal components, I'm just going to close this wavelet one, just so we don't get it confused. So the way we get these is we turn our functional principal component scores. So this table here, we take the first, let's see, I think for this example, we would only need 4, but let me see. I'd actually used quite a few. But for each functional principal component score, so each row in this table, we're modeling each column as a function of day, month, and year, right? So we can predict the FPC score for a different combination of day, month, and year. And then we use those predictions to weight these functions and then put them together, right? So Ryan had a nice slide where it was basically the mean function plus a weight times shape function 1, a weight times shape function 2, and we added up down the line. What we're doing here is just using those supplementary variables to predict the FPC score that we use to weight these shape functions. I wish I had a good slide I could show. Ryan, I don't know if you happen to have yours convenient, but you had a nice slide that
Play? While
that showed that.
Play. While Ryan's looking for that, could you just go to your functional PCA red triangle menu there and just change the number of functions to 3, just to make it nice and small? Okay, so now we're only using the first 3 shape functions, explaining about 86% of this, right?
Yeah.
So now, if you show your FPC profiler, which is right there, and now your DOE profiler is right below this. Okay, with those two on the screen, I often describe this as we're basically fitting the bottom 3 here. Okay.
Yeah, that's right.
Using these to model those 3 lines up there, and what's making those lines are those columns of FPC scores.
Yep.
So this is
that's
the
right, Tom.
model of that model.
I can share that slide if you want to see it.
Yeah, that'd be helpful if you had a handy.
Yeah. I think there's a few different ones. Like this is an actual function that it's showing you how it's kind of getting back to using the functional principal components to reconstruct the function. And I think one thing it's good to remember, whether it's functional DOE or just functional PCA in general, it's an approximation to those fitted models that we have. So the kind of the residual plots, the actual by predicted plots will be degraded, as you kind of go down to this approximation. And then you get kind of another level of degradation as you go to the actual functional DOE. And I think it's a similar story with wavelets, where you have, this nice wavelet model. You kind of skip a step by not doing functional PCA, and instead of you model coefficients directly, but to make it tractable, you don't use all the coefficients. You kind of use the ones with the most energy, so to speak. So it's, now that's a degradation in kind of, it's an approximation, and then the fits to that are a further approximation. I think the biggest motivation on our end to do the wavelets DOE is to have perhaps some more interpretability. You could find that this particular wavelet coefficient is what was driving, some change, and that would mean something to a practitioner potentially.
Thanks, Ryan. But Tom, that's a good stopping point for me if we want to take a break.
Sure, let's do that. And it's 2:38 here, so we're going to do about 10 minutes now. We may be early for whatever snacks they're putting out, so we may take a break. Maybe we won't go a full hour if there are good snacks. So let's just try to be back here in 10 minutes then from right now, and we'll get going with the next section Clay and Ryan have. Okay, we're at about 10 minutes on that break, so if we can get going again. And I'm not sure if Clay or Ryan is up next, but
okay. It's still me, Tom.
Okay, still got direct stuff to do, don't you?
Yeah.
Okay.
So I'll try to speed up through that part.
You're doing okay.
Just
on time.
But I wanted to touch on the wavelet DOE thing one more time. I tried to put together an example. So let's say my function that I care about is a function of time, and I've got three, design factors, so x1, x2, x3, and I've sort of rigged it up so that this coarse coefficient is a function of x3. My resolution 1 wavelet coefficient is a function of x2, and my last resolution 3, second to last resolution 3 coefficient is a function of x1 and x2, right? So this is kind of simulated in a way exactly like what we're trying to get at with wavelet DOE. So as I change x1, it changes that resolution 1 coefficient, and this is how my reconstructed function would change. As I change x2, it changes that resolution 3 coefficient, right? So this is one of my experimental factors, and it's only impacting this small region of my reconstruction function. And then x3 is kind of controlling where the intercept is, right? So my third experimental factor is just shifting my reconstructed function up and down. So that's a simulated version of what we're trying to reproduce with wavelet DOE. We're trying to get at these kinds of relationships between our wavelet coefficients and our experimental factors. So hopefully that was helpful as well. But now we're going to shift gears out of wavelets, and we'll take a look at what we call in JMP direct methods. And I'm gonna try to go through these relatively quickly so that we still have time for Tom to show some examples. But direct functional PCA and JMP, it's been around for a couple versions, and it doesn't impose a basis function, right? So there's not a wavelet, there's not a P spline, there's not a B spline. It's just acting directly on the data, and because of that, it's quite fast. So what does it look like in matrix form? Imagine if each row or each function that we care about is the row of a matrix, and we just stack them up. So that first row of X is function 1, the second row of X is function 2, and the last function is the last row of X. So when we do direct FPCA and JMP, it's basically just an SVD of that data matrix X. The SVD loadings are a lot like what we call shape functions in the FDE report. The function summaries table is a lot like the SVD scores, and the singular values are similar to the eigenvalues in the functional PCA report. And they're off by scales. That's why it's not exactly a one-to-one mapping between SVD and direct FPCA, but it's a similar, it's a similar idea. But then I find it hard to, when I was learning multivariate statistics, I didn't really understand why we needed an SVD. And a lot of it came down to, we were taught SVDs, if you have P columns, we used a full dimension P SVD. So we were using an SVD with the same dimensions as the data, and I never really understood that. But what is an SVD? Why do we want to use an SVD to look at functional data? Just to remind ourselves what an SVD is, it's a decomposition into scores and loadings where that matrix U is it's orthogonal, and D is a diagonal, and V is our matrix of loadings, and it's orthogonal as well. And back to my point, it's most interesting when we're using fewer dimensions in the SVD than we have rows or columns. So we're really doing dimension reduction. And if you think about how to calculate an SVD, I only share this because it'll be more pertinent in a minute. You can kind of stack up those so that it looks like a linear regression. If we hold V fixed, we can rewrite our SVD so that it looks like a linear regression to solve for U. And then if we hold U fixed, we can rewrite the SVD so that it's a linear regression to solve for V. And so that's one way that you can do an SVD. You can get starting values for U, hold it fixed, and do least squares to solve for V. Hold V fixed, do least squares to solve for U, and just keep going until we converge. And that's not the best strategy, but the reason why I mention that is it's easy to modify that, and we'll see an example of that in just a minute. And we use SVDs in a whole lot of ways. Here, you might tend to associate SVD with principal component analysis, like the multivariate. When you're thinking about multivariate analysis, and we're looking at candy bars. If we look at the loading matrix of a PCA, here we'd see that the strongest loadings for principal component 1 are calories, fat and cholesterol. And that's kind of the first dimension, is qualities about fat and calories. And the second principal component, the high loadings are on vitamin A, C, and calcium. So the second principal component is like vitamins and nutrients, which with a candy bar data set, there's not a whole lot of those. And then the third principal component is related to the serving size, and it's really just kind of the size of the candy bar. So principal component analysis, we tend to think of as a dimension reduction technique. The SVD is too. We're taking a lot of information and compressing it and using less information to represent it. And so the SVD is particularly helpful for functional data because we can rewrite rows, the rows of X as a linear combination of columns of that loading matrix V. And that's how we get our reconstruction from an SVD. We use this relationship here. And just to sort of visualize it, let's say we have a really simple V matrix. This is what V1 the first column of V1 looks like. Or this is what the second column of V looks like, and this is the third column of V. So our reconstructed functions from those loadings vectors, they'll just be linear combinations of those. And so here's an example. We can take V1 plus V2 minus V3, and this red function is one of the functions we could get out of these blue loading functions. So what happens within the FDE platform is we subtract off a mean for each column, and then we do an SVD of the data. So when we reconstruct the function, we take the mean and we add the first singular value times the first score times the first shape function, and the second singular value times the second SVD score times the second shape function. And we can think of the SVD as a deconvolution, right? We have multiple functions and we're adding them together. That's a convolution, and the SVD is a way to undo that. And some things to consider about an SVD. Usually every element of U and usually every element of V are greater than 0 in magnitude for all of the elements. They tend to take positive and negative numbers. So if our shape functions are, our shape functions are going to take positive and negative numbers, even if our original data that we're trying to model only takes positive functions, those loading functions can still be negative. And then, so these qualities aren't necessarily ideal for functional data, and that's why we've added some new methods in the Functional Data Explorer. In particular, we added penalized SVD, non-negative SVD, multivariate curve resolution, and a different flavor of multivariate curve resolution. So let's take a closer look at those. But first, a little bit of inspiration that I take. Here's a quote from, if anybody's watched Parks and Recreation, there's a character named Ron Swanson, and he says this about, working hard to get nothing done. And I see parallels with that in my career. I've spent a lot of time working on variable selection techniques in JMP. So if you have hundreds of predictors and you don't want them all, you only want a subset of those meaningful predictors. I've worked really hard so that we give you back 0 a lot of the time, right? When you do variable selection, you're essentially setting some of the regression coefficients to 0. So I've worked really hard to give people a lot of zeros in my day. And I think it's kind of funny. It's kind of similar to what Ron Swanson says here. But so we talked about the scores always taking non-zero values. So here we see we've got an FPC score close to 0. We've got another one close to 0. And these blue values that I've circled, it would be nice if those were exactly equal to 0. That would make our decomposition a little bit easier because we would know that our first function was really only a function of FPC1 and FPC2, and we could just drop out the third shape function. And likewise, it would be nice if regions of our shape functions could be exactly zero, right? So this blue area that I've circled here, that's not exactly zero. It would be a little bit simpler if it was exactly zero. And so there's been a lot of research into zeroing out parts of an SVD, right? So it's called sparse SVD. There's a couple different names for it, penalized matrix decomposition. There's been quite a few methods proposed to deal with this kind of data. And so we implemented the method in this one here by clustering via sparse singular SVD. We liked it because it doesn't require cross-validation. It's easy to use an information criteria, which just makes it faster and easier. But the key to this method is sort of, earlier we talked about doing alternating least squares. Well, now you can do alternating penalized least squares, and that'll set some of the elements exactly equal to zero. So earlier we talked about alternating least squares. We're just going to do alternating lassos, and that's how we make a sparse SVD. So you can see when you use a sparse SVD, now some of your FPC scores will be exactly equal to zero. Some of these regions will completely be not meaningful. They'll be exactly equal to zero, but we give up orthogonality. So that's something that you would need to consider before using a penalized SVD. Another thing about the SVD, like I mentioned, if you have strictly positive functions, it's possible that some of your shape functions will take negative values, right? So here on the left, all of my data are strictly non-negative. All of them are above zero. But when I do direct FPCA, some of my shape functions take negative values, right? They dip down below zero. And that may not be appropriate depending on what we're trying to do. So that's why we've added a non-negative version of the SVD. And instead of doing alternating least squares, now we can just do that. You think about doing non-negative least squares. So we constrain the regression coefficients to be strictly positive or zero, not strictly non-negative, I suppose. And again, we give up orthogonality in both U and V, in both the scores and the loadings, but that might be worth it. That might be worth it to us. So now, if that same example, that same example, we have strictly positive data here. We have strictly strictly non-negative shape functions, and we have strictly non-negative scores as well. So our decomposition is a little bit more meaningful, maybe because we're adding up zero or positive combinations of these shape functions. We can also do a penalize, just to save time, I'll sort of skip over these, but you can also penalize the non-negative SVD and get a similar result. But the nice thing about the non-negative SVD is it sort of stabilizes things on its own. So by adding a penalty, I haven't found that you're gaining a whole lot. So you'll notice a region like this. Here, this is the non-negative SVD, and this is the penalized non-negative SVD. You'll notice these regions are a little bit flatter than they are down here, but it's not a huge difference. So I wouldn't expect, huge differences between a non-negative SVD and penalize non-negative SVD. You can also rewrite that SVD framework to be a little bit different. You can rewrite it instead of UDV. Now we just have C times S transpose, and we're going to constrain rows of scores to sum up to 1, right? So this S matrix is still our shape functions, and these are still, we can still kind of think of these as scores, but the scores are going to add up to 1 for every row. So it's like a mixture of our shape functions, which can be really nice. And it's especially popular with spectral data. So this is an example here where each function is a spectra for a carbohydrate, and we know that we have blends of 3 different carbohydrates, ribose, lactose, and fructose. And we want to figure out the mixing proportion of those. And multivariate curve resolution is exactly designed for that kind of problem. So if you go into the Functional Data Explorer, which we'll see in a second, it's just a menu option there, and you can choose the number of components. So we knew that we wanted 3 mixture components, and we can just ask for that in the dialog. It's also easy to accommodate pure spectra. I'll just show an example of that here in a second. And most of the time when we talk about multivariate curve resolution, we want the shape functions to be strictly non-negative. But that's not necessarily always going to be what people want to do. So there is a variation where you can allow your shape functions to go negative. So here, with this unconstrained multivariate curve resolution, we still get shape functions, or we still get scores that sum up to 1, but our shape functions can take negative values as well. And depending on your setting, this is a better option than regular multivariate curve resolution. So let's take a look at some examples. So this is the carbohydrate data set that I was talking about. And we see we have 3 what we call pure spectra. So we know that one of these is just ribose, one is just lactose, and one is just fructose, right? And so we can tell the platform that we know that by marking those as our validation set. And we specify our spectrum, but by marking pure as our validation set, we're only going to train our decomposition on these 3 rows, right? So under direct models, we have multivariate curve resolution, and we want 3 components. We could just ask for 2, but we know that we have 3. So let's take a look at our summaries. So by marking those as pure spectra, we know that the first row is just 100% FPC1. The second row is 100% of the second shape function. And the third observation is 100% of the third. And then everything else, we're sort of back solving to figure out those mixture components. So this 4th spectra is about 80% of the first component and about 20% of the second and almost none of the last. So it's a lot like an SVD, but we're constraining these components to sum up to 1. So what if we didn't include those as pure spectra? We could just look at the entire data set. We'll take that away. And so now we're sort of ignoring that we have that information about pure spectra. And we can sort of get at the same thing. So the first is about 97% of the first component, and so on. So these, like I said, these will always sum up to 1. And because I used regular multivariate curve resolution, these functions will always be strictly non-negative. Let's see. Here's a, we're going to revisit the Slinky Dog data. One way we could look at this is using a non-negative SVD, right? So let's try that. We don't need that many dimensions. So let's say we want a non-negative SVD with 5 components, right? So we're going to use a non-negative SVD to model these wait time curves. And so let's take a look at our shape functions. This first one is kind of like just an afternoon rush, right? There's people in the morning, or there's not a whole lot of morning contribution, not a whole lot of evening contribution. It's mainly midday, right? This second shape function is like the morning rush. This third shape function is like the evening rush. And then this fourth shape function is like a severe morning rush, and so on. And one of the nice things about this is you can kind of think about just hordes of people getting in line for Slinky Dog Dash. So this corresponds to the morning rush, the evening, and so on. And it's kind of a cool interpretation as you add more components. And then again, you can do functional DOE, so it's the exact same idea. We're just going to use linear regressions to predict these FPC scores, and then combine those with our shape functions to reconstruct those curves. And the nice thing is we're guaranteed that that these predictions will always be positive, right? Because we are combining positive functions, so these are always going to be within the realm of the data we observe. We're not going to get any negative wait times, so that's kind of cool. Yeah, I kind of sped through those. Were there any questions about these direct methods? I wanted to leave time for Ryan and you, Tom.
Okay, I'm not seeing any questions in the room. I guess some comments I would make, or even questions to ask, are the direct methods, are they partly driven by speed?
Yeah, for sure. And just not wanting to impose any kind of basis function. Wavelets are pretty flexible, but we're still making, we're imposing a certain type of shape to them. With direct methods, there's no shape that we're trying to satisfy.
Okay, and then what has been, I would say, the driver for adding these capabilities? I mean, is it coming out of the spectral analysis customer base, or, I mean, I only saw the MCR for the first time last fall at the Discovery Summit, and I applied it to like that mineral data I showed in the morning, and it actually worked really well with that. So it was sort of like, oh, it seems like there are going to be some data sets that's well suited.
Yeah, absolutely. So multivariate curve resolution definitely came from requests to do that sort of mixing problem, right? You know that your functions are mixtures of shape functions, and wanting to back solve to get those proportions. it's I think it's a pretty popular technique for people dealing with spectral data.
Okay, I don't know if this is the best place to ask this question or maybe closer to the end and after Ryan's presented, but if someone was new to this and they come to this Functional Data Explorer platform and would you have any guidance for them to say, try this first? This is something that's simple, straightforward, robust, and or does it become, here's some good books to read?
Well, I think Ryan and I mean, we might have different opinions. I think I would tend to lean towards using wavelets the most. They're super flexible and fast, and I'm also just biased because I happen to work on that part of FDE. Whereas Ryan, do you have a different opinion?
I mean, I don't know that I have a great start here opinion. There's so many things that, at least within our software, that we can kind of attack, that it's really just dependent on the type of data you have. If it's really simple, you should probably start with a B-spline. If it's more complex, you should start with a wavelet. If you need a lot of cleaning up, there's a lot of tools to dig in there, and that's kind of.
The other thing to keep in mind is if it's really not appropriate to grid your data, to sort of force that assumption that your data are on a regular grid, then wavelets and the direct methods are probably not. It's probably a non-starter, right? I wouldn't even consider those. That would be more appropriate for a P-spline or a B-spline.
Yeah, and I do think the gridding question, I mean, one of the, I felt like, strengths that was purported for functional data at the beginning, back in JMP 14, was the fact that you didn't need to have your data collected on a regular grid, that it could handle the fact that things were on a different, it ultimately maybe the same range of time, but not collected, uniformly spaced in time.
Right.
So,
yeah, so no matter what, it can put data on a grid for you. It makes it really easy to sort of overcome that hurdle. But whether or not it's appropriate to sort of force it onto a grid is a separate question that's sort of problem specific.
okay, I don't know if that sparked any thoughts in the room. We have a hand that went up.
Thank you. Yeah, hi. I just had a question about the non-negativity constraints you're mentioning. So, of course, it's a sufficient, I guess, approach to enforce the non-negativity of the weights. But are there any circumstances where it's better to enforce the non-negativity on the output and to let kind of the latent weights be unconstrained?
That's actually a great question that Ryan and I have talked about, and it's something that we've meant to come back to. Just in terms of the way that we've implemented these in the software, we have the fitting tools to do exactly what you've said. We just haven't played around with it yet. But that's something we've been meaning to sort of follow up on.
Okay, I don't see any more hands up in the room, so if you guys want to continue on.
Well, Tom, we're getting close to the end, right? I have a little bit I could show. It's not a lot. I think your case studies would probably have the most impact if we're kind of running up to the end, if you want to go ahead and do those.
Tell you what, I'm going to ask you to finish up whatever you have. I mean, even
Okay.
if it's just 10 minutes, let's do that, and then maybe we'll take one more break and come back and do some case studies.
Okay, you guys can see jump, Tom?
Yes.
Okay, great. So what I was just going to kind of show is kind of one other side fork in the road you can take in analyzing functional data that we've added into our software. And that's this idea of peak finding. It came up a little bit earlier about, why would you kind of use a summary of a peak or something else? And it's kind of really based on the problem that you have. So just to kind of get an idea of how you launch into this, in this data set that we have, so we have some chromatograms that we want to try to connect these flow rate and temperatures to, and we want to get an idea of how are these things impacting, the shapes of our chromatograms, the kind of locations of peaks, some area under the curve measurements. Can we separate peaks out? So we have kind of this data set is all of our rows are functions. So it's pretty small run here. This DOE just has 10 rows. And we have these different batches, and we have some combinations of flow rate and temperature that were used. And then I kind of briefly mentioned this, but we can now have, these kind of column names are kind of the X input space, and each one of those cells is the Y response value that we have for the chromatogram. So that's kind of what filled into here. So by default, you'll get this kind of initial data view. So we have some initial data, and I think Clay showed some of this. So we wanted to align on the maximum of our data set. And then we wanted to filter down into a specific range between -1 and 1 to get kind of these curves that we're interested in. And our goal is to pull out peaks from the data and collect summaries about them that we can use in predictive modeling. So you can launch, there's kind of a peak finding option if you have JMP Pro 18 that will launch you into this peak finding window. So when you launch it, you have this ability to add peaks yourself. Kind of, we have a whole editor that you can use to add peaks, remove them, change set specific values for your peaks. And we also have some kind of visualization tools to help you see kind of multiple functions at one time, or kind of zoom in on one function and kind of flip through those. Kind of the heart of this, and I have some slides on kind of what this does, but Clay covered wavelets enough, I think. So what's really happening with this automatic peak detection is we want to find locations of peaks. And what it's using is the continuous wavelet transformation to basically hone in on where those peaks are. So if we run that, we can kind of look at our different views. We have now tried to identify locations of peaks, kind of starting and ending points. If you imagine thinking about taking the inverse of this data set, you can think, oh, now I'm finding these kind of troughs, which are peaks on an inverted scale. So we kind of apply this two times to try to find where these things might start and end. And in this data set, we have really only 2 peaks that we're primarily interested in. So we can go in and we could select these by hand and remove kind of these kind of nuisance peaks at the beginning. But we have this, what we just call automatic peak removal, where I can specify a value that any of the Y values below this will get rid of those peaks. And in this case, the number 1 million does the job, and it gets rid of those initial peaks. So there's not really much else we want to do here. We're kind of satisfied with kind of the bounds that it found on the peaks and the locations of them. So this takes us to the summaries that we want. So we have area under the curve metrics for each of the 2 peaks that we have, if we have them. Kind of this first one only has 1 peak. We can't really separate it out well with this particular technique. But from that, we can get the widths of the peaks, also the heights of the peaks, and then this idea of a half height. So if this is kind of part of your problem space, you'll be familiar with trying to resolve peaks, and this half height is a function of the resolution metric is a function of these half height widths and locations. So the idea is, if you think about, okay, this was the location of my peak. What if I take that Y value and divide it by 2? That might be right around this region. What's the width there? So we are providing like this overall width, but now this idea of a half height width, and is helping us learn about the resolution between peaks if there's multiple of them. So one issue with this that you'll see is that some of the half-height widths for the second peak are gone, or we're unable to compute them, and that's because we don't really have great separation. Like in this case, we can kind of think about what a half-height might be, but this is really kind of a fully empirical kind of technique that in future versions of the software, we have some parametric models that will allow us to assume that maybe this has a Gaussian shape, so we can directly acquire those metrics. But in what you would be able to use now is it does not have that for you. So it's kind of brought to life what we're calling peak difference. So it's very correlated with what a resolution might be, but it's, what's the difference in the peak locations? So if you kind of needed some quantitative measure of resolution that wasn't fully, the kind of classical formula, we have something available that you could use. So as you could in other parts of this software, we want to save these summaries out. We don't have anything directly built in to help you analyze it like we do with functional DOE, but what we can do is we can save them out so that we can try to build some sort of predictive model. Now, we don't have a lot of rows here to do anything too fancy, but we do have our supplementary variables, and we might be interested in seeing how those are affecting area under the curve, these widths, and then the resolution metric, which is kind of the notation here as it's saying the resolution between the kind of index 0 and index 1 peaks, so just those two that we have. So if I just bring up fit model, I can just like to use generalized regression because it always behaves nicely. But we are going to use our supplementary variables as kind of our inputs. And we're going to predict, let's see, we'll do the two area under the curves, and we will do locations. Oh no, we'll do area under the curves and resolution. And so by default, it's going to do a standard least squares. So let me pull up the profiler for this. Oh, wait, maybe I do just use regular fit model. Call standard least squares. Separately. Okay, so kind of all of this is really to highlight that you can, fit some models in other platforms in our software, or if you're using other tools to try to understand as I change these two knobs that I have access to, this flow rate and this temperature, is that helping me get better separation? So the kind of the general story here is that as you increase flow rate, the two areas under the curves are going down, which, as you might imagine, is creating better resolved peaks. And if you increase the temperature, you kind of create smaller areas under the curve for that first peak, but slightly larger ones for the second. So you're just kind of shifting kind of where that resolution might live up and down. And that's kind of this is like the very far reaches of functional data that's, not necessarily, you won't find this in like Ramsey and Silverman, for example, but something that has come up that there's a lot of interest in, these kind of summaries specifically about certain aspects of peaked data that we have made available. And, if you need references on this, you can look at the continuous wavelet transformation with peak finding. I have a reference slide I can pull up. This is kind of if you need some references on kind of what's kind of going on under the hood here. But I'll take any questions on this if anyone has anything.
Okay, I'm not seeing any questions, but I realize we're getting near the end here, and I almost feel like we should have asked some other questions at the beginning. So you're nearly done with this short course on functional data analysis, and I feel like there's two main things we've talked about in terms of data. One being, do I have sensor data, okay, or do I have spectral data? And I feel like the spectral data tends to be more the chemist world, and maybe sensor data is maybe more a manufacturing engineering world. So just if I could get a show of hands, how many people here have spectral data? Well, okay, in my mind, I'm thinking it's more like, is it NMR, Raman, mass spec? It's rather than being created from a mathematical analysis, it's more of a chemical analysis. Maybe to me, that's what I'm thinking of. So I only saw a couple of hands go up. And so realize that a lot of the people using JUMP are in biopharma, chemical, oil and gas. There's a lot of people. I think DoD is not so much working with that. So I think a lot of the course shows you what you can do with spectral analysis. And I wanted to ask if, I guess I didn't ask the other question, how many people have some type of sensor data? Okay, that's at least half the room stuck their hands up. But I also wanted to ask Clay and Ryan maybe to talk a little bit about the roadmap for where they see the functional data platform and functional data analysis going over the next release or two. I know we have a release coming in the fall.
Yeah, at a high level, there are just some tools related to spectral data. We have a new baseline correction tool that we have. There's an existing baseline correction tool, but it's a manual process. You have to go in and kind of move things around, and these are more automated things like the SNP procedure or a reweighted least squares procedure that will remove baselines automatically for you if those are impacting the data that you have. And the other thing I briefly mentioned in what I just showed is this idea that if you do have peak data and you cannot resolve peaks, you want to assume some kind of model underneath the hood. And so we have parametric peak models kind of coming up. I don't know, Clay, if that kind of covers the highlights.
Yeah, I think so.
Okay. Again, anybody in the room have any questions at this point for Ryan or Clay on the things they've shown? Okay, well then, why don't we take another, we got a question coming up.
So this is a question inspired from the Slinky Dog example. So I imagine when you set some of those knobs that there's of course variability on where what your waiting time would be at any given hour of the day. And it got me thinking, is there a way to do that sort of analysis, but instead of looking for a conditional expectation, you look at a quantile or something? I'm curious if you guys have seen that or have thought about something like that to add to your platform.
So we do have tools for doing quantile regression, but so what you're describing is almost like a wavelet through a wavelet quantile regression type smoother, which is super interesting. I don't know if that I don't know if that type of thing exists, but it'd be cool to check into. Yeah, it's a great question.
Another question for you.
To capture the uncertainty in your predictions, can you bootstrap that response and then maybe get some idea of what the variation is?
Yeah, you certainly could do a bootstrap. You would just need to do it in such a way that didn't break the structure of the functions. You could still, if you're trying to fit a function and if you bootstrap just kind of randomly over all functions, maybe a function drops out or you only get, say, 1 point from a function. So you just have to be careful to make sure that that doesn't happen. I don't think, Clay, correct me if I'm wrong, if we have a clean way to do that by hand and jump, but I know you can do it with our JSL scripting.
Yeah, so I think the way to do that would be with a parametric bootstrap, essentially like adding noise to the data over and over again, that kind of resampling. But that's right. There's not currently an easy way to do that within JMP.
All right, if there's no other questions, let's take one more 10-minute break, and we'll come back, and I'll try to do a few more case studies, and hopefully you'll come back from the break. Okay, I can't remember if I said 3:46 or 3:48, but you know, the sooner I get going, the sooner we'll be out of here, if that's okay with everybody. And so I had 2 slide decks that if you downloaded the contents, you'll be able to find things. And I think not everybody was here right at the start this morning. So I do want to point out again that there is a Word document with about 45 links to videos. And in this, the one slide deck where I featured the reverse engineering, the formulation this morning, I had this one slide that has live links on it as well. And so the top half of it would have content similar to what Ryan covered this morning. Okay, so sort of the more introductory functional data analysis. And then there is a section on an introduction to spectral analysis there as well. And then the 3 case studies are what I covered the reverse engineering formulation this morning, but there's a full 45-minute, technically speaking, session on that I did last fall. And then I'm going to talk a little bit about some of those other ones here. And then I also pointed out there's 2 other recordings there, one from Curtis Miller, who's actually here, and then some folks from the Army Chemical Biological Center. And once again, there is the full Word document where, again, I have tried to spell out who it is, how long it is, what year they did it, so you sort of know what's newer, what's older content, and a lot more ideas here to see. And I will point out there is a 12-minute video there, a deeper dive into wavelet models for functional data analysis by Di Michelson. She's on our JMP education team. So again, if you're looking for a nice explanation of wavelets, that if you wanted to show that to somebody, you could track that one down. And then I also wanted to point out there's kind of a section here, this Spectrus section. This is an add-in developed by one of the other systems engineers, Mike Anderson, who is a spectroscopist. And so it does things that are different than functional data analysis, but also if you do have spectral data, can help you make more sense out of it. So that's in the JMP Marketplace, where you can download that add-in and add it to JMP to help you get more out of it. Okay. With that, one of the questions that came up was about the optimization process. When we say, hey, how do I find that sort of optimal curve? And it was this example that Ryan covered earlier. I changed the data a little bit, changed the specs a little bit. It's a similar story. We had the same figures there. But basically, here you can see there's a designed experiment on the left, but I have some confirmation trials that aren't actually used in the fitting. I'm very big on, because I'm not a statistician, I'm all about fit the model, and can it predict this stuff over here? And if it can't predict this stuff over here, I don't trust the model. So I'm all about running those checkpoints. And here I use the term golden curve analysis. So the yellow curve that you see sort of diving into spec and getting flat immediately, that's not real data. That's my dream data, okay? That's what I'd really like my data to do, even though I know it can't. And so that's what my target is. I put it in here, and I'm calling it my golden curve data. So once again, this is a very simple data set. A B-spline with 1 knot does a great job. You can see the red FPC score, which is the largest positive FPC. That is the one most like a hockey stick and the highest up. And then there are two that are very similar that have low negative values, minus 56 and minus 60. Those are the lowest curves and also the most round. So you can sort of see the extreme, because this is a very, very simple example of how that number is actually telling us something. Okay, and then here are just examples of, as I move between the case with the high positive and the low negative, whoops, you can see how much that curve was changing. Okay, so again, there's the high FPC1, so it's a high hockey stick. The prediction's 124. When it's a large negative value, it's got a low prediction of 85. Okay, if you also look, you can watch the factors here, and you'll see that between the positive 79 and the minus 60, you're going to see a lot of change in the factors that make a difference. When I get to the minus 60 and the minus 56, you're going to see that flow changes, but flow doesn't do very much. Okay, so here you can see the only factor that's changing between those two cases was flow, and flow doesn't do much. So there's not much difference in the curves, where here you can see it's actually the percent beads and the percent active are both changing, and those are the ones that have the biggest effect. Okay, now we're going to get to the part about, I want to do that golden curve analysis. So if I were doing it in JMP, you know, here's that data set, and I come down here to my, let me hide this. I go to the point I've done my, I get my functional principal component profiler, but again, FPC1, I don't have a knob in the process called FPC1. So what I want to do is model that as a function of these four factors here, okay? And now I can see what the difference is. But if I hit this button that says optimize target, I guess I was already optimized. Let me take it out of optimum. So when I hit optimize target, it moves the curve into the spec limit and gets into spec as soon as possible. That was our goal, the golden curve. Okay? So what did it do to pull it into spec? And this is where if I click show the target profilers, you can see here, and I'll make these a little bigger. Okay, I've got the top row is the profiler we've been looking at. Okay, so it's the shape of the curve, it's got the spec limits versus the four factors. And then there are two other rows. One is the difference from target, which is row 5000 or batch 5000, and the other is the integrated error from target. So when things are not optimized, so let's just move things away. Okay, you know, these are big numbers, and when I say optimize, it tries to find the set of conditions that minimizes that error from target. Okay, so that's what's happening behind the scenes when we do that optimization. And a question came up earlier from Charlie, where he said, can you ever get trapped in like a local optimum? How do you know you're in the global optimum? And I think the answer was, well, you really need to try it a few times, but I would make the point, particularly in this case, you know, you've got a very, very simple function. And when you look at the target profilers, wrong one, down here, the target profilers, you know, these shapes are not terribly exotic, okay? It's when you have multiple, like, spectral peaks that you can get trapped in a local one. So you can almost look at this and know whether you have that potential to get trapped, okay? So going back to the slides on that. So here's the before picture, before we minimize that integrated error from target. And so, again, this desirability is turned on in this case, and desirability is on a scale of 0 to 1, and so you can see here that the only one that we're using the desirability in the optimization is the minimize the integrated error from target. So it's got a negative slope. What we want is as low a value as we can get for integrated error, and that's what's going to drive the optimization. And then this is just showing the before and after of that. Okay, and then this is just, so at this point, this is very much what like Ryan did. I can manually move this, you know, if I don't want to use the optimized target, just I could find a set of operating conditions, that puts that curve into spec as soon as possible and also tries to keep it in spec, which is another part of the goal of that golden curve. Okay, so, and I have like all the steps I did in JMP to make that happen. So if you want to try to reproduce that, the data set is in the files that we sent people. Okay. Any questions on that? That's kind of a review of what Ryan did, but a little more conversation on the optimization. Okay, so that was functional response DOE. The other method that I think I feel like I see a lot of this, is I'll call it more of a functional response machine learning method. So here we're going to try to use the curves to predict something, like yield of a batch, or probability of detection, or failure, or hit. So the case study that we feature is, again, a data set that has been modified and simulated, but it's actually from one of our customers, and they had a process where they were trying to seal these silicon wafers by putting a piece of glass over it, and you put it in this device, and you put some force on it, and some vacuum, and some flow, and some voltage, all these things to make this seal. Okay? That's great. The problem with this process was they were typically making about 12% of the wafers defective. Okay, we'd like to improve the yield. The real problem is, because you can't electrically test this wafer yet, you won't know for weeks that you've got a defect. So wouldn't it be great if I could look at these 5 sensors and right now say, there's a high probability we've made a defective wafer or not. Okay, so that's really the driver behind this. And so there's 122,000 rows of data, so there's 2,000 wafers, each with 61 time steps, and we're measuring the charge, the flow, the piston force, the voltage, and the vacuum. And so here's what the data looks like in the profiler. If you sort of connect it with smoother lines, basically anywhere there's a rainbow showing up, there's information. Where there's no change, there's really no information there. Okay? So I'm going to focus on the flow response, but when I do the actual analysis, we'll do all 5 at once. And so earlier we talked about what is functional data analysis, and we often talk about here the responses now are these functions. So the curve is our fundamental unit of observation. And by now I think this story is probably getting old, but the whole point is that we break this curve under functional principal components into 2 pieces. We've got shape functions, and we've got these scalar quantities, these FPC scores. And so I'm highlighting row 17, where if you take that minus 150, okay, so right here, you take that value, you multiply it times this shape function, okay, take this minus 2.94, multiply it by that shape function, we add both of those to the mean, I can reproduce the shape of 17. Okay, so you've been seeing that. So this is the function-to-function variation, and this is the longitudinal variation. Okay, and then this just is an animation sort of showing what's happening. If I put my cursor on that little step at the front, you saw that FPC1 makes a big difference. And if I put it on the top of the hill, so there's 2 places where there's information, right here and up here. So when I'm on this little step, notice as I move FPC1, I can make that be a positive step, or I can make it be a well, okay, just based on where's the FPC value. And if I do the same thing on the top of the hill, I can kind of make that step a little higher, or I can make it be a little bit of a well. Okay, so this is a nice one because you can really visually see it, and I've got some static shots over on the right showing the impact of the FPCs. Okay. Well, if we take all 5 sensors and we do this analysis, we ended up with actually 12 different FPC scores that we would want to use to try to model the wafers. Remember, we've got historical data here. So we've taken these 2,000 wafers, we've broken it into 1,000 of them for training, 500 for validation, and 500 for testing. Okay? So the good and the bad is we know it was a good wafer, we know it was a bad wafer. So we might do a neural model, okay? We might also do a regression model. I think this one's a lasso model, so it's basically, it's a good or a bad is the end result here. And so, I did it both ways, and if I look at my, sort of truth matrix at the bottom, how well did I do in my training, validation, and test sets, knowing the test set had absolutely nothing to do with fitting the models. And you'll see that the number of misclassifications on the left is 50 and on the right it's 49. Okay, so they both missed about the same amount. And so now I can take that model, one of them, and I'll take the neural model, and I've got this probability of it being good or bad. Well, I've highlighted two bad rows. Notice the top one says just misses being good. In other words, its probability was 0.49, but had it been 0.51, it would be green. Whereas the other one is 0.25, so it's far from being a good wafer. So, I don't want to lose that information. So one of the things that we can do is actually ask JMP to do a decision tree on that probability from the neural network, and it gets these cut points where you can see if that probability is 0.75 or higher, out of those 839 wafers in that bucket, 96% of them were good. Whereas in the below 0.395, there's only 42 wafers in that bucket, but 95% of them are bad. And so that middle bucket, which is between 0.395 and 0.754, it's about a 60-40 split. And so here's where, as a manufacturer, you have a decision to make. Are we just going to chuck them anyway because it's not worth spending time? Or is it worth it, since about half of these are probably still good, spending a little bit of time sorting them out and putting them back into production? But at least you've got your 1,000 wafers, you've got a decision as to what you want to do. Clearly throw these out, clearly process these. These other ones maybe we want to inspect a little bit. So this is just, how would I do this here in JMP? I've got my probability of good. I've got the sort of just red-green result, good, bad, from my neural model. And then on the right of that, I put in I call it my stoplight rule, where I now know, ones that are really bad and which ones are, not necessarily bad or good, but they're somewhere near that 50% probability. So I've turned on this inspection sort of light for those. Okay, the rest of this just basically bears out the fact that whether you did the generalized regression stoplight rule or the boosted neural rule, you got about the same quality of results at the end. So again, these would be the steps that you would go through with that anodic bonding to try to make that, to do that analysis. And happy to get in and drive that a little bit just so you can see this working. But any questions on sort of that approach? Okay, the difference between that one and the ball mill was the ball mill, we're trying to predict the shape of the curve. Here, we're trying to take the curves and predict an outcome, which in this case was good or bad wafers. Okay, and then I might as well knock these off here. Just some functional data analysis performance tips. These are a few years old, so everybody's computer is faster, but still, when you've got thousands of batches with thousands of measurements, things can slow down. Certainly, probably since this slide was made, they added things like wavelets, which are really fast, and direct functional principal components analysis, which is also very fast. But before we had those fast methods, we might want to, try just smaller sets of data and see how things are working. And when we find things promising, go back in and use the larger data sets. We might also try subsampling down, particularly, if you've got a curve and for whatever reason the sensor's picking up data every 1/10 of a second. Really, if you had every second, how different would that curve look? You'd have to make that decision as to whether you're thinning. But the idea is try to fail fast in your modeling process, and then once you've kind of got things so you're understanding things, then go back and throw all the data in, even though it might take longer to do that analysis. Okay. So I wanted to make it through those slides a little bit and go back out. Okay, so let's get rid of that. Okay, so here's that anodic bonding data where you can see I've got 122,000 rows of data there because I've got these 2,000 wafers. And again, I've taken that data and broken it into, 1,000 for training, 1,000 for validation, 500 for validation, 500 for test. And then here are the 5 sensor readings. Okay? And so if I were to, again, with JMP, if you have seen us doing this, you can save analyses to this upper left panel. So if I click this one that says FDE 5 sensor P splines, it's going to automatically do the analysis for, if I've hit it, there we go, for all the sensors at once. And let's just see how long this is. Okay, so, I don't know, 15 seconds or less. But notice I've got a tab for each one of those sensors. So, here's where you've got an F-35 with 20,000 sensors. I'm not sure you're going to have 20,000 tabs here, but, you want the few sensors that are relevant for whatever feature it is you're trying to model or predict. So let me pick on the flow example to again show you the steps here where, here's where some of the variation is, and here's where a lot of the variation is. So when I do my model, looking for this section right here, you can see that 97% of it is that first step, and only about 3% is that top step. Okay, so at this point, this is where we could open up all of these, and if I look at this area called function summaries, you can see that there are 3 function summaries here, but we've seen that the third one really doesn't do very much. So you'd want to go in here, and you can either do it right here. You might want to change that, I would like to change that number to 2. And then if I look at the summary information, which I get right here, by default, it actually gives you all these other columns of information: mean, standard deviation, median, min, max, integrated difference, root integrated square, root integrated function square. You can have all those columns go over too to help you with your modeling if you want. Okay? Here, I purposely have said deselect all the summaries and then said just save the formulas, and I only want to take the first 2 FPCs. So I would go through, and I'm just going to click OK here. I would go through the other 4 tabs and do the same thing. I'd say, this one might have 4 or 5 FPCs, but I only want the first 2 or 3 because those dominate things. And when I'm done with all of the above, after sorting that all out, you can come up here and go to a Save Summaries, and then you get that table with, as you can see here, the only one I really adjusted was the flow FPC to have 2. Well, there's 2 charge FPCs. Looks like there were 3 piston force. There were, looks like, 9 vacuum FPC. That would have been a good one for me to cut that back probably. Okay? But then this is the table that we'll use to build our models when we try to predict whether or not, it's a good or a bad wafer. But, I would want to focus it down to the sort of critical few FPCs in each one of those sensors. Okay. Any questions, comments on that anodic bonding example? Okay, I've got one more for you, and then we'll be out the door here. Okay, this data set came from a colleague of ours, a systems engineer in, I believe, the Netherlands. And so I've recycled it. And let me go to the slides first. actually, I have one more example here. I'm just going to describe it because I'm not going to actually do anything with it. But I mentioned this earlier that, you know, I first learned about functional data 18 years ago when I was working for the Army. And this is that data set. And notice we have these Gaussian plumes. But again, you know, I'm just a skeptic. I always want to break it into a training, validation, and test set and see how well can I predict those green curves. And notice here, this was an example, did not have wavelets at the time, but Fourier basis did better than B-spline and P-spline with this particular data set. So I tried them all, did it. You can see I've got 90 small curves over on the left. I actually had 7 FPC scores, because you'll notice their contributions here. I'm at 43%, 71, 84, 93, 96, 98 to 99. I probably could have got by maybe with just 93% and only 4 FPCs, but I wanted to keep everything. Now, this was the deterministic simulation. So when it comes to the DOE factors here, they're labeled X1 through X6. Those are things like wind speed, wind direction, time of day. All of these things affect the viability of a biological agent in a cloud, you know, as it moves across terrain. Well, all 6 of these factors were fitting. Okay, so all 6 of these fit each one of these 7 FPCs. And because it was a deterministic simulation, I actually used the Gaussian process model. But that's not built into JMP, so I had to sort of manually make that happen and then, you know, stick those functions into this. But what we end up with, again, is the ability to, you know, here is a test trial, so it wasn't used in the actual analysis. So the circles are the data, and the smooth curve is the functional data curve. So it was a little bit off on location, but the right height. Here's another trial, 16, got the location better, but didn't quite get the height. But, you know, this functional data ran a lot faster than the neural modeling I had been trying, and I felt it was kind of comparable. Where there were issues, and you'll see it right here, on the very front edge, you get kind of an artifact there because the real data is going along at 0 and suddenly the cloud arises. You know, it goes from 0 up. It doesn't do a dip and like a little wave on the front end of it. So that's something I haven't revisited this data in quite a while, but now that we've got the wavelets and some of those direct methods and the non-negative methods, I'm going to probably attack it and see if we can't do a little bit better. Okay. And so this last example is you can actually have functional data as both the input as well as the output to your model. And in this case, it's this glycemic response model. So here's what we're going to end up with. We want to predict a patient's response over time after they first fast and establish a baseline over time, and then they consume a snack. Okay? So what we're looking at here is the curve we expect their monitor to say for the next 4 hours after they eat a snack. And so these two FPC scores over here are really, are coming from, we have fit the baseline information to get those FPC scores. Okay, so here maybe gives you a better idea. The blue curve is the baseline. They consume a snack there at time 0, so we're going from minus 600 to 0 for 10 hours. They consume the snack, they get that glycemic response spike, and you know you can see the red curve, and after about 4 hours it's subsided. So there's the data for about 20 patients. They were eating either 3, 4, or 5 snacks, so we've got a lot of baseline information when they eat the snack. You know, if we look at the overall average, you can see that, okay, it kind of just barely slopes down for those 10 hours, and then there's very clearly a spike when they consume it if we average over everybody. But what I wanted to do was, again, isolate 4 of the patients, so Craig, Eric, Ryan, and Travis, highlighted in yellow. I'm going to exclude them and use them as my test patients. And I'm going to fit the data for the other 16 people. Okay, and why did I pick these 4? Some of them had a single peak, some had a double peak, and some had moderate variation, and I wanted to include the one with the smallest variation and the largest variation in my test set. So once again, there's the smooth data for the snacks by the patient, and now we want to create that model. So both of these, because they're functional data, can be fit where we will get out shape functions. Okay, so we've got the shape function on the front end, and we've got a shape function on the back end. The extra information is we've got these FPC scores. The ones on the left are going to be X's, and the ones on the right are going to be Y's. And the one other piece of information is what was the snack. So the model gets built by fitting the FPC scores on the right as a function of the FPC scores on the left, as well as the snack they consumed. Okay? And the end result of that is we have a model where we're predicting the shape of the curve after they have their snack based on which snack did they consume and what were the settings for FPC1 and FPC3 for that particular patient. Okay, so again, the model is, here would be this validation row would be a patient for which we want to make a prediction. So we're going to take their FPC scores. You actually take the test panel patients and you put them in with the original data so that FPC scores get developed for them as well. They're not used to determine it, but they're used to predict it. And then we'll use those three as the inputs to the model. And then these are just examples of copying and pasting that FPC score on top of the raw data. And in some cases we did okay, others, particularly when there were double bumps here, we didn't do as well. But I basically just did it for all of the patients. And again, this is several years ago. I look at this data, I don't see it as, boy, wavelets is going to help it very much because it doesn't have that much structure to it. But some of the new direct methods, particularly the non-negative, those might make sense because I would expect these data to be non-negative. Okay, so that's just kind of shown it that way. Let me just go to one last graph.
I have a question.
Sure.
For data like that, do you need to tell us where you wanted to split? Do you need to know ahead of time, or can you?
Yeah, so what I did, I had the data for the full 14 hours. I took all the data from time 0 when they eat the snack, and I hide and exclude that temporarily in the file, and I say, okay, take the 10 hours of before the snack, and let's get an FPC score. Let's do functional data analysis on the before part, and that way I get the FPC scores for the before. Then we know when they take the snack, and then we also can fit the curve after. So.
I guess you're asking, so in this case, you kind of know the time is based on when they eat the snack. But if you're just collecting data and say all of your time order, they don't align with all the different curves, is there a way for JMP to look at all of your curves and pull out where you can make that switch? Does that make sense?
Well, the short answer is yes, but there are alignment methods. Would it make sense to align the peaks? We can tell it that. Would it make sense to align the starting points? We can tell. So there are things we can tell it to align. There's another feature called dynamic time warping that I've not really used myself, but there are methods to try to make things align better if they're not greatly aligned. I can tell you where things struggle a bit, and I have a current customer in the Army that sent me, an image of their analysis saying, we're struggling with, we've been using functional data for a while, it's been working well, but with this data set it doesn't seem to work well, and their problem was some of the curves stop really early and some go really long. And it's important to them that they know when things start. And so they know this stuff doesn't line up well. And at this point, for them, it's not working as well as things have in the past. So, we're looking to see, is there some type of an alignment method that could improve their analysis? So generally speaking, if everything's over the same range, I have found functional data to work very well. As you start to get to, there's less and less alignment between all of your cases, you're going to have, things will struggle a bit. So here, I think the important thing is, this time is completely relative to each patient. They didn't all have to start fasting at the same minute, and they all had to pop the snack at the same minute. All that matters is they fasted for 10 hours, popped the snack, and we recorded the 4 hours afterwards as to what was the glycemic response. And then we're just aligning the data all relative to, here's when everybody ate the snack. Is that good enough answer? Okay. So within here, that's not the one I wanted. Here it is. So here they've actually color coded this in such a way as you can see on the left, here's the before, oops. Here's the before curve, you know, up here's the after curve, you know, there's that time 0 in the middle, and then here's the snack information, and then here in the orange at the bottom are the before FPCs. So as I move these, okay, you can see I'm getting changes in the before curve, which is just going to be associated with a patient with that FPC score, and then the after curve is going to be driven by both the FPC1 and FPC3 values and the snack value. So if I change this, the snack choice makes no difference on the time before curve in the blue box on the left, but it makes a big difference in the time after because it does depend on the snack that they ate. Okay, I'm going to stop there. No need to drag it another 7 minutes now. Okay, but I want to thank everybody that hung in here all day. Those of you, if there's anybody left online, we appreciate you watching. Please send feedback. Again, I'll put up the very first slide with, if you haven't noted our contact information. But if you're here at the conference, stop me, ask me questions. Happy to try to answer. If I need to get to Ryan or Clay to get an answer, I will. But we appreciate you all listening to our functional data course. Thanks.